We're going to end chapter 3.3 talking about exponential notation or exponents and the role exponents play. Again, math is a language, so exponents are articulating something. We use the exponent to describe or try to explain a mathematical operation. So we've already talked about addition, subtraction, multiplication, and division. We know addition and subtraction are related inversely, right? They can be used like missing add an approach to solve a subtraction, to solve an addition, multiplication and division, missing factor approach, right? There are ways that they're linked together. And so exponents are linked to repeated multiplication, right? Where remember, multiplication was repeated addition, division is repeated subtraction. The use of exponents is the idea of repeated multiplication. And so when we do a multiplication, right, there's the idea of repeated multiplication. We're multiplying factors together, right? The numbers being multiplied together are called factors. And so in this second example here, 18 times 18, right, you see repeated multiplication. And you'll see these examples here, looking at this here, right, multiplication. Now, I want to start to think about, is there a shortcut notation we can use to articulate it when it's repeated? And the answer is yes. That would be when we start to use exponential notation to do that. So here's kind of our definition. A number raised to the power of n. And again, we're talking about whole numbers here right now. Later on, we'll look at negative exponents. That would be chapter 8. But for now, we're looking at whole numbers. And so you can see a to the power of n equals a times a repeatedly multiplied together n times n factors of a. N is called the exponent or power. A is called the base. A to the nth power or a to the power of n is the language we would use. And again, we're talking about whole number exponents. In advanced mathematics, we use negative exponents, we use decimal exponents, fractional exponents, right? So, but right now, whole numbers. This example is completed. Hopefully that makes some sense. I'm just wondering what questions, if I was in class, I just show that and then have students ask me, because I know you've seen this before, but again, hopefully you're in a space to ask questions, right? To recognize the patterns that are being displayed here. To the power 6, to the power 3. Notice they're grouped together. Only the y's have repeated multiplication, so only the y to the power of 3. Here there's a little group. This reminds me a little bit of algebra, so you can see how that gets grouped together. Notice how they're grouped together. All of this leads to rules of exponents, stuff you probably maybe dreaded in algebra or didn't understand where they came from. We have the product rule, quotient rule, power rule of powers, power rule of products, power rule of quotients. All can get confusing. In the end, I want to make sure it makes sense. And this is where hopefully you get a chance, and I'll show you in the book, to see the proofs in the book of each of these. But here on the right are some examples. And notice the shortcut notations to add them. But the key question is, why does addition work? Now, the way to think about it is if you wrote this stuff all out, that's where it would start to make some sense, right? If you wrote it all out, you would see then that, that makes sense where the short would be to add, because you would end up adding there would be 11 factors of 3 being multiplied when you wrote it out. Similar here for the division. If you wrote it out, what would cancel or divide into ones? The common factors would divide into 1, and you're left with 4. Then there's 6 on top, 2 on the bottom. You're left with 4 of them, so 4 to the power of 4. And then here again, 5 squared would be 5 times 5, and then 3 times, so that'd be 5 times 5, 5 times 5, 5 times 5, 3 times, which produces 6 factors of 5. So the same idea could happen here. Notice this is a multiply, not a plus. So you can turn this into 14, right? And then 14 squared, or you could see that this would be 7 squared times 2 squared. This would probably be used more in an algebra sense, because I would probably just do 7 times 2. But again, remember, these rules sometimes are leading towards further use in advanced mathematics, specific in algebra classes. So take a look at that. You're going to get to the textbook and take a look at for each of these as we get through it here in the textbook. Oh, right here, there's little proofs to kind of explain where that comes from. So I think it's really worth clicking on, looking, and seeing where these rules come from, at least these first two rules, and then you'll get an intuitive idea of where these other rules come from. And then we have this example. Go ahead and try to practice that before you look at my solutions. That would be awesome to do that. But there's the questions, and then there's the solutions. Hopefully it's straightforward with respect to, again, the rules that we're talking about, right? And you can see I wrote out where you add, where you multiply. But again, it's not just the process of adding or multiplying, right? Or subtracting. You are doing something that makes sense in the shortcut. Anytime we think of a shortcut, just know that there's some sense making that needs to be made. So whenever there's a shortcut, you should ask why. Why does this shortcut work? And your students may be curious, especially if you end up teaching like a sixth grade class that's getting to pre-algebra. You'll have students ask questions, and you want students to ask why, and you want to feel comfortable being able to answer the why questions. Zero is an exponent. That's always a tricky one. So let's go ahead and take a look at that. We have a kind of a definition for that. Zero is an exponent. Anything to the power of zero equals one, as long as a is not equal to zero. And I'm talking about right here, we could see, right here, we could see zero as an exponent, as long as a, so anything to the power of zero. Now, why is that? There's a little explanation here of why that would be. We could see x, it's hard to read on the video, but this is on your notes, x to the power of n divided by x to the power of n. We know the same number divided by the same number equals 1. That's right there. Now, we also know x to the power of n over x to the power of n, right? We could subtract. It equals x to the power of 0 because we would subtract, right? The rule is to say n minus n, which equals 0. So if x to the n over x to the n equals x to the 0, and x to the n over x to the n equals 1, then we get the conclusion that x to the power of 0 equals 1. Something to look at, think about. Hopefully that makes some sense, and you can see it up here in my explanation on top also, how you could see x to the n over x to the n equals x to the 0. So anything to the power of 0 equals 1. And then we end this section similar to division by 0. What about 0 to the power of 0? Sounds like it looks like a cool number. I would challenge you to put that in a calculator. Again, this goes back to being undefined because of a pattern. Using inductive reasoning, we come up with potentially two different conclusions here. Pattern 1 and pattern 2 over here. I'm not highlighting them. Pattern 1 and pattern 2. 3 to the power of 0 is 1, 2 to the power of 0, 1 to the power of 0. So looking at the pattern, you would think 0 to the power of 0 should equal 1, right? The pattern indicates that as we decrease the base by 1, keep the exponent the same, it all equals 1. So yeah, equals 1, sounds cool. But if we do 0 cubed, 0 squared, 0, 1, it all equals 0. So we think 0, 0 equals 0. So which one is it? Well, because we have two conclusions based off of inductive reasoning, we just say because of this inconsistency, right? There's a contradiction here. We say 0 to the power of 0 is undefined. So that's the answer, even though it feels like it could be 1, it could be 0. It almost feels too good, like it should, but it doesn't.